All right. So hydrodynamics. Um, I have zero experience in this thing because most of the questions that I thought I could solve, I actually cannot solve with the amount of knowledge that I have. So I had to learn some new stuff to actually understand what the question asks, right? And what are the assumptions that you can make and you can't make. And yeah, all right. So let's explain everything first of all. So you have the fundamental equation of hydrodynamics of ideal fluid. So ideal fluid is any fluid that has zero compressibility. It has zero viscosity, which is important because we'll be using that. Right. Yeah, that's an ideal fluid. And the Eulerian equation, that's what they have given us. So this is basically rho dv upon dt is equal to F minus del P. What is del P first of all? So this del operator, okay, this thing is basically just this partial the pressure upon partial x in the x direction, then partial P upon partial y in the y direction, and partial P upon partial z in the z direction. All right, that's what this del operator actually is. Okay, and the way this thing is derived is basically from F equal to ma applied on a cube of the fluid, right? So yeah, to F equal to ma, and you will get this equation. So here dv upon dt, that is actually how the velocity of that particular block changes with time. So this is not partial v upon partial t because v would be the flow velocity at a particular point, or u would be the flow velocity at a point. When we say dv upon dt, we actually want to figure out the rate of change of the velocity of the block, not of the velocity at that point, right? So this dv upon dt can be written as partial v upon partial. I'm going to use u. So u vector will be our flow velocity at a particular point. So partial u upon partial t plus so the other part, that is like the other part basically tells us how the um, your velocity is changing of this block, all right, but it's changing because the block is moving in the fluid, and then at different places of the fluid you have different u vectors, right? So because of that, how much is your velocity changing, right? So that will just be, first of all, how much is it moving in the x direction? That's just ux. Now every, let's just say dt seconds, it moves by ux dt in the x direction. So it's change in the velocity, that will be partial u upon partial x times dx. So dx upon dt, that's just equal to ux. And then similarly for all of the other directions. If you want an in-depth derivation of this thing, um, this is called like the what is this called, by the way? The material derivative. Okay, no, the, I think, convective derivative, right? That's what they call it. Anyway, if you want a good derivation for this thing, do it yourself. All right, that's what I would say if I didn't have a video that is actually describing how this equation is derived in the first place. So go watch that first, right? Right. And this thing a lot of times is written like this: ux dot del. Okay, sorry, u vector dot del, and this applied on u vector. So this is just kind of like shorthand notation for this whole thing. You don't need to actually take this operation like yeah, you don't have to think of del vector as an actual vector. No, it's not. It's just something that we use to make our equations less take up less space on the page, right? That's all it is, nothing else. Okay, so now we have written this thing. Yeah, and you can just plug these into this equation, right? These expressions, and then there you go. You have your equation. There's also the representation of this equation in the cylindrical coordinates. So yeah, but that's something I won't do because we won't be needing that most of the time. All right. Okay. So that was nice. Now that I've explained this equation, let's go to the next equation. Oh, and actually I didn't explain what F is, right? So F is the volumetric density of the force at that point. What that basically means is dF vector upon dV. So suppose at that particular position that you are, you just take any block of water or whatever you fluid you have, and then you measure the force, the external forces, other than of course the pressure forces acting on it, and you see that the force is equal to the force is equal to, let's just say, d capital F vector, and then you divide that force upon the volume, right? So divide by what divide by the volume, which is just dV. So what you get, the expression that you get is what they are calling a small F vector, which is just partial F vector upon partial V basically, right? So you can think of like F vector being the net force on a volume, external force of course. So then as you increase the volume by partial V, sorry, dV in some particular direction, you increase the volume by that much, how much does the force increase? I know this is very vaguely described because there are like multiple directions where you can increase the volume, but you can think of it like that. Okay, and for most cases where you don't have any crazy amount, any crazy forces acting on the liquid, your small f vector will be the same thing as rho g, because the f vector acting on our the df vector acting on our dv volume is just its gravitation, right? Which is rho dv times g, g vector actually, right? So yeah, this small f vector will just be rho g. That makes sense. Okay, then you have Bernoulli's equation. So it says that in a steady state flow of an ideal fluid, this um, expression rho v squared upon 2 plus rho gf plus the pressure. And here we are using the pressure everywhere. What does the pressure actually mean? It means the static pressure. So say you have, I don't know, a river flowing, and you put your finger in the stream, you will feel a pressure, right? Or let's just say you don't put a finger, you put something like, I don't know, some flat surface. So yeah, like maybe some kind of pan or something, right? So you have a pan, it has a handle and everything, whatever you have, just put that into the river. If you put it just like that, you will feel a force in that direction, right? But if you put it like this, you won't feel anything, right? Because yeah, there's no area on which you have pressure, although there is actually the pressure on this thing, but the force, net force goes out, that's just zero. So what is happening? What pressure are we talking about? Are we talking about the pressure that we got in this case, or in this case, or what are we doing? Well, it's neither of them. What the hydrostatic pressure means is that if you just leave this pan, I mean let it flow with the river, then the pressure exerted by the water molecules, which are just doing random motion on the pan from each direction, that will be the same, and it will be equal to our hydrostatic pressure, which we'll call P everywhere. So this case will actually have the pressure P from these two surfaces, from this side and that side. It will not be the same pressure. It just so over here you got the hydrostatic pressure plus the dynamic pressure. Over here I don't know what it is, but yeah, that's what will happen, right? So say you have water running in a tube. So if you hold the tube, the pressure that you will feel, that is in fact, I mean, yeah, like if you are holding the tube, I mean, you are the person holding, or let's just say, how do I explain this? So the tube ends over here, and then you're just holding a very, so you're holding like some kind of sheet that doesn't allow water to flow through, and you are the one holding this sheet into its place. It's rolled up, and then you are holding it, right? And then water is going from here to here, and then it's flowing out. So the pressure that you will feel, that's the hydrostatic pressure, because there's no dynamic pressure involved. There's no uniform motion of particles that are hitting on the surface. No, it's only the thermal random motion, right? That you are going to feel. So yeah, that is the hydrostatic pressure which we'll be using everywhere. So this P hydrostatic pressure, this P hydrostatic pressure. All right. Now that I've explained that, let's go to the Bernoulli's equation first of all. So it's saying rho v squared upon 2 plus rho g plus P equal to constant. Right. So this is done using energy conservation. That's how you get the derivation of this thing. But then energy conservation is along only one streamline, and that's why they are saying this equation is true only along one streamline, right? So along any streamline, you have this equation. But if you go from one streamline to some other streamline, you might not have this happening because the constants for those two streamlines might be different. Now, there is a condition though that we'll be actually using everywhere, which is that if what was I saying? Yeah, this equation only works if the blocks of volume that you're taking, right? So like you have water flowing in that streamline, right? So throughout that streamline, the blocks of water that you're taking, they only have translational motion. They don't have rotational motion. So there might be possibility that along this streamline at some particular point, you have a kind of like a vortex, right? So there's water flowing around it, right? So if you take the volume element in here, what will happen is that um, right, this system will have some angular velocity, and because of that, there's that degree of freedom that you have to consider. And then yeah, this volume will also have rotational kinetic energy, right? Of course, there's the thermal energy also linked with the potential energy that you will have, which we don't have to. When I say the potential, I'm not talking about gravitational potential. I'm talking about the interaction between the molecules. But let's not go into that. So the thermal stuff, yeah, the internal energy, we don't talk about that. Like this block, it's moving. It has an average velocity vector along this direction. So there's half mv square because of that. There's the internal energy, right? There's also the rotational energy. So all these combined, when you consider everything combined, that's how you get the final kinetic energy, right? So suppose your streamline doesn't have just the translational velocity and it also has angular velocities everywhere, then that's a problem, right? Because you can't apply energy conservation anymore. So this thing is not constant anymore, right? Yeah, that's a bit of a problem. Okay, but if you don't have this angular velocity anywhere, so angular velocity is also called I think it's called the vorticity, right? Because of course, like it's related to having a vortex or not, or being a part of a vortex or something like that. So that basically only tells us that you can apply this equation everywhere, right? So the condition for this equation to be applicable, it's that the vorticity should be zero at every single point along the streamline. And actually, the vorticity, it's like this. Your omega vector is like the curl of our u vector. This might look weird at first. What is this? But yeah, that is that's the way it is. In fact, that your omega vector. Look, this volume is so small that you can't get the omega vector meaningfully from the u vector directly. So you actually have to rely on partial derivatives to get your omega vector. So this operation del cross, it's called the curl, right? So this operation, it's curl of u vector. Does that make sense? Right. So this, if it is zero everywhere throughout the streamline, then you can apply this equation. And also there's a theorem, which is, I think it's called Kelvin's vorticity theorem, or something like that. I don't know. What it basically states is that if you have like water or any kind of liquid, which is having zero viscosity. So if it is flowing, and when I say zero viscosity, what we should say is that we are assuming it has zero viscosity, and also that the conditions for that assumption are met, right? So yeah, if you are in a region where that condition is true, that you can assume the viscous forces to be negligible, right? You're assuming that viscosity is zero. In that case, if your region had no vorticity at first, and then if you proceed along the streamline, I don't know, maybe the tube is going like this or whatever is happening. Maybe there's like two parts now after some time. I don't know what's happening, but if you go along a streamline, I have no idea how these streamlines should be. Yeah, maybe it's like going, I don't know. So if you go along any streamline, and there's no viscosity, then in fact there's no way that you can have vorticity along the streamline anymore. So what it basically says is that if initially you had zero vorticity, then throughout the streamline you will have zero vorticity. So yeah, that's what it says. And in fact, to prove that theorem, you need to know a lot about these del operators, and it just really, yeah, complicated because there's a lot of algebra and just a lot of partial derivatives everywhere. So, and also a lot of these del operators, and that's the main problem that I have with you know presenting to you a derivation of this fact. I can't because I'm not on that level yet. I only know the meanings of these operations, right? I don't know their properties. And yeah, so the thing is, all you have to care about is the fact that this condition is met, that at some point you have zero vorticity for the streamline, and that there's no viscosity, or we are assuming that viscosity is negligible, right? That condition is met. If that happens, then yeah, like there will be no angular velocity, okay, no vorticity throughout the streamline, which means you can apply the Bernoulli's equation throughout the streamline. And also, if you find a region like this where all these streamlines have the same constant, right? So yeah, this constant, it's the same for this streamline, this streamline, this streamline. All of them have the same constant, and then this condition is met that there's no vorticity. Then even if like the streamlines diverge or whatever happens to them, we can still take points on these streamlines and say that yeah, these like this value, so rho v square upon 2 plus rho gh plus the pressure, these two are still the same things at this point as well as at this point. And that is something that we'll be using a lot, because everywhere that will be calculating anything, first assumption will of course be that viscosity is zero, right? I mean, wherever we'll be calculating with the Bernoulli's equation. Because if there's viscosity, then yeah, there's like, you can't apply energy conservation anymore. So of course we're assuming viscosity to be zero everywhere, which means, and yeah, like we will just have the water flowing from a tube initially with all these streamlines having the same constant in any case, right? Look at these have the same pressures everywhere, right? There is gravity, and because of that the pressures are different, I know that. But like, come on, is that so complicated? No, right? Just assume the tube is very thin, and then you can just do it. Yeah, that makes sense. And even if the pressures are different, you can still apply Bernoulli's equation along one streamline, and then you can trace back and then compare how the pressures change, right? So that you can still apply the Bernoulli's equation for these 2 points. That is, if you know where the streamlines start from, which is once again a kind of hard thing to do. But yeah, if your tube is thin, just assume there's no difference in the pressures, because our rho gh term, it will be small. So what that means is that we can just apply this equation everywhere. Yeah, isn't that just awesome, right? Oh, and by the way, like when I said there will be difference in the pressures, there will be the opposite difference in our rho gh terms themselves, right? So actually that would mean that these constants are in fact the same already. We don't have to think of a very thin tube. You can already apply the Bernoulli's equation in every single case. Oh, yeah, well, I didn't think about it till now. So you know how they say that when you start to explain things to other people, your own concepts get more clear. So okay, so you can apply this equation throughout the fluid without having the care if your viscosity is zero. and your initial flow was like this. So there's all these streamlines which are parallel, and yeah, okay, then you can do this thing. And of course, they should have the, well, should they have the same velocity? I think they should, right? Because otherwise, how can you do this? I mean, they will have, of course, they will have the same uh, velocity, right? I have never seen a question where the velocities are different. And that's why I'm assuming. And okay, if their velocities are different, then that means there's a gradient, which means there's viscous forces. So yeah, that explains why we can assume the velocity will be the same everywhere. Okay, so that's good. Now we know how the Bernoulli's equation works, and although they are saying along any streamline, it's actually along. So on any 2 points of the fluid, you can apply this equation. It doesn't matter that these are on the different streamlines. You can still do it. Okay, next thing, which is, what's this? The Reynolds number defining the flow pattern of a viscous fluid. So this I haven't, done in detail, and I don't know why they use this thing, but yeah, like the Reynolds number is proportional to uh, the inertial forces upon the viscous force, if that makes sense. So viscosity, of course, this is related to the viscous force, and rho VL, that's like kind of like inertia, not exactly, but that makes sense, right? And L is just a characteristic length for a tube. This length is just a diameter, and eta is the fluid viscosity. So when the Reynolds number it exceeds a critical value, your flow starts to become turbulent, right? That's what this is used for. Yeah, and when that happens, of course, your speed just becomes a critical value as well. So at VC, you just have REC, which is the critical value at which you will have turbulent flow starting, right? Okay, then you have Poi Series law, which says the volume of liquid flowing through a circular tube in meter cube per second. So this is when you have viscosity, right? So R and L are tubes, radius, and then whatever. I mean, we can derive this on our own. No big deal. Um, yeah. And so delta P upon Q, that thing is called the fluid resistance, which is of course just 8 eta L upon pi r power pi r power 4, right? And L is what? L is the length of the tube, of course. So I mean, look at that. It's just 8 L upon pi r power 4 times eta. That's what the resistance is. Yeah. So usually the way you have resistance is like you have rho, so some resistivity, some constant, which depend on the fluid or whatever, times the length upon the area. That's the way you have resistance in, let's just say, currents, right? So electricity and everything. You have resistance in this form. In this case, though, you have r power 4 over there, so you can't use this, right? You should actually have like maybe rho L upon A square, but yeah, the main thing is that this is the resistance. It's given by, I mean, uh, yeah, like it is actually defined as delta P upon Q, and its value is this thing. Okay, cool. Then you have Stokes' law. Till this date, I don't know how this thing is derived, and most likely I will never know, because yeah, it just seems like this was probably done using experimentation. I don't know how this is derived. Maybe it can be derived, right? I mean, we have this equation. You can use this along with, okay, so adding some viscous terms as well. And yeah, also another thing I noticed is that viscosity that I was familiar with, that was explained to me in schools, right? That is very different than the kinetic viscosity that you actually have. So in the kinetic viscosity thing, you have del square of u vector involved. But then I thought, like, why is there partial squared ux upon partial x square in the viscous force? Because, so like, if you have this block of water moving with some velocity v, and this is moving with some like v plus dp thing, and this is moving with v minus dp, I don't know, something like that, right? Yeah, so you have this happening. Then how is there viscous forces acting? It doesn't make sense, right? Just along x, if your velocity, which is also in the x direction, that's changing, how is there viscous forces? I didn't understand that. But now I know that viscosity is not the way it's taught in schools. Instead, it's actually like it's a combination of momentum diffusion and also the actual intermolecular forces, right? So the reason for viscosity, at least in ideal gas, would be that these blocks share molecules constantly, right? So they have a habit of exchanging these molecules, and then molecules from this block have higher velocity, and over here they have lower velocity. So when you exchange, what happens is that some of the higher velocity molecules go into this, and the lower velocity molecules come into here, which slows this down and speeds this up. And talking about the average velocity, all right? So it increases the average velocity of this block, and it decreases the average velocity of this block. And that's why you have viscous force, right? And when we say pressure, that is different from this phenomena, right? Pressure is basically because like collisions are happening. Yeah. So that explains it. Okay, cool. So now we know that. Okay. Uh, so maybe using this equation along with the viscous terms added in there, um, and some boundary conditions, you can probably prove this thing, but I won't. I just won't. Fine. So now we can start. So 315. Ideal fluid flows along a flat tube of, so it's a flat tube. What? A tube, and that's flat. Okay. Of constant cross section located in the horizontal plane. Fine. Horizontal plane. Flat tube and bent as shown. Okay, they give us a figure. 1.8. Oh, I have seen this figure on some of my tests, although I've never been able to solve this question, right? Okay. Yeah, so top view. The flow is steady and the pressures and velocities of the fluid equal, okay, of the fluid equal at points 1 and 2. Sorry, what are the are the pressures and velocities of the fluid equal at points 1 and 2? What is the shape of the streamline? Streamlines, yeah. Okay. So once again, assume that there's no viscosity, right? Now you have, okay, these are the same speeds everywhere, and it's what? It's flat, right? Okay, the tube is flat. Ah, interesting. And then you have this happening, and so think about a single streamline. How would it be? Okay, you know what? This bent shape, it looks like a quarter circle to me, doesn't it? And we know that this just continues. So this kind of distribution continues till this point, and this distribution continues till this point, right? So it's like this. You have this arc, which is basically a quarter circle in this case. All these u vectors are the same, right? All these u vectors are the same. Okay, interesting. Yeah, and now we need to figure out what do we have to figure out? Of course, the pressures and velocities throughout this region. Okay, this is kind of weird. So these streamlines, how would they be, first of all? You know what? Okay, what if I extended this kind of this? Okay, what if I extended this to? Okay, that's not doable because we don't know whether or not these velocity vectors are going to be the same throughout. Uh, I think you can assume there's some symmetry to this thing, and then let's just say that the streamlines are in the form of circular arcs or something. It could be, right? So if the streamlines are of like it is the shape of the streamlines are just circular arcs, then using the continuity equation, you could just say that throughout this streamline, your speed is the same, right? Yeah. Okay. I think that we can do for each streamline. Not exactly. Okay. No, that's not always true. Huh. Like some sort of thickness or something. Yeah, this is weird. How do we prove that it's like that? I don't know. What is the shape of the streamlines? I think these are circular arcs. If these are circular arcs, then by the symmetry along our angle theta, you can just assume that the speeds should be the same everywhere, right? Because why would this speed be different than this speed? And why is there a difference, first of all? I don't think there should be. Okay. Oh, and you can also apply Bernoulli's equation or something. Yeah. What if the pressures are different? Yeah, pressures could be different, right? I think it's just the starting question. How could it be complicated at the first question itself? Maybe it could be, who knows? Uh, but I'm starting to think that maybe you have the same speeds throughout this streamline and the same speed throughout this streamline and the same speed throughout this streamline and so on. So basically, like at any given point, your u vector, it's pointing in the tangential direction and it's the same magnitude everywhere. So, okay, very weird. So you just have u vector is equal to ut hat. That's the distribution that you have, right? Okay, and of course there's the equation of del dot u equal to 0, so that should be satisfied. And at the same time, okay, there's like no viscosity, but there could still be vorticity, so Bernoulli's equation might not be true. Who knows? Yeah, there could be vorticity, right? Of course. And I don't want to get the curl and the divergence operators in the R vector thing. I really just don't want to do that. But I mean, okay, I have a video explaining how you can write a divergence operator, um, like in the cylindrical coordinates, right? Which is what I did after I saw this question at first. So till then, like, sorry, till now, and after that time, I have just been looking everywhere for explanations of these equations and yeah, things like that, right? So I even got an expression for the divergence operator in the cylindrical coordinates, and I guess you could use that, right, to check this. Oh, and I didn't actually explain what this equation is. So this equation, this basically says that the divergence of the flow that is 0. So it's basically this thing, partial ux upon partial x plus partial uy upon partial y plus partial uz upon partial z equal to 0. And when I proved this at first, what I did was that I just used the incompressibility of the fluid and then just took a volume, right? So a volume along any kind of streamline. And then I just figured out what its change in volume will be if you have like the rate of change in volume will be for some, you know, some distribution of u vectors, right? So that's why we get this thing. Okay, you should just watch that video of mine where I actually explain everything in detail. Yeah, so this equation should be satisfied for any incompressible fluid, and we'll consider water to be one of them. So is this going to work? That's our question. I'm really just guessing a solution and then seeing if that solution is going to work or not, right? And if it works out, perfect. What's the big deal, right? Yeah. Also the gradient. Okay, what was the thing? Ah, God, I'm just forgetting everything. Am I not? So the gradient can also be actually written using cylindrical coordinates, if I remember it correctly. So in the divergence, you had an extra term in the gradient didn't. So in divergence, usually you just have like partial ux upon partial x. Now you just have partial uz upon partial, because that's the only Cartesian coordinate that's still in the cylindrical coordinates. Then you have so partial ux upon partial x plus partial uy upon partial y. So if you just go blindly, you might say it's like partial u r upon partial r plus partial ut upon partial p, which is more like r d theta, so partial theta, right? You might say it's like this. But then the thing is, actually you need an extra term, which I don't remember. What was it like? I think it was 1 upon r, and then something else in there, like involved. What was the thing? Why can't I remember it? Was it like ut upon, I think, yeah, that was the thing. The t hat vector, and then the derivative of the t hat vector is what you had to do. So that's why you got that, right? Yes. So it was this thing, I think. Ut upon r. Was that the thing or not? Maybe it was ur upon r. Oh god, I just don't remember it. Oof. But anyway, this is 0 for this distribution. This is 0 because the speeds are like, okay, the radial speed is 0 in any case. Was it ut upon r or what? Why can't I remember it? I don't think it was ut, it was more like ur, right? So there's the ur vector that you will have, which is along the r hat direction. You want the partial one partial theta of that thing, right? R hat changes, of course. And then there's also the t hat changing itself. But okay, if this is with respect to theta, then okay, now this is getting complicated. But I'm sure I did have an extra term, right? And I mean, this does this look like that any point you have positive divergence or negative divergence or something like that? No, it doesn't look like that, right? I mean, everything just flowing, so divergence must be 0. So then maybe it was just ur upon r. Look, I don't want to derive it once again. I think this was a thing. Yeah, it must have been. That's what I got the last time, right? Okay, so then it's just ur upon r, and then ur is 0. So, that works out. Oh god, I really just don't remember anything, don't I? Huh. Partial ur vector upon partial r. I think that was. Oh yeah, okay. I think I remember something now. Yeah. So this is like it should actually have been this thing, partial upon partial z plus actually not like this. It's comma partial upon partial r comma partial upon it's like partial theta, but then you have this 1 upon r, and then you have this vector dotted with our, yeah, this vector, right? So which is just uz u. I know I'm not putting them in the order that they should be in, but whatever. So like it's actually this thing, so taking the dot of this thing. Yeah, okay, right. I think that makes sense. Oh, okay, like it's supposed to be this thing, sorry. Z hat partial upon partial z plus r hat partial upon partial r plus, right, okay, this was what I got the last time. Yes, and this dotted with our u vector, right? And our u vector is of course just um, u r r hat plus u t t hat plus u z z hat, right? So now the thing is, um, right, so we just have the dot product, right? So partial upon partial z of this thing, well, that's just 0. Not 0, but okay, this dotted with r, so z hat dotted with r hat, that's gonna give us 0 in any case. So right, this started with this whole vector actually just gives us this thing, partial uz upon partial z. Then you go for this one. So right, partial upon partial r, right? Does t hat change with changing r? No, it doesn't. T hat changes with changing theta, right? Yeah, that's the thing. So this is still going to give us partial ur upon um, partial r. Then you have this thing. So partial upon partial theta of ur. Okay, all that stuff. But then you have t hat and r hat. Yeah. So the first part of this derivative that will not give us anything. But then the other part, so partial 1 partial theta of r hat will be involved in there, which is t hat. So that's why you get this extra term. And then when you try to do this with this, so you will have partial t hat upon partial theta that will involve r hat. So r hat dot t hat, that gives us 0. And that's why there's only this term, right? So it's supposed to be u r upon r, right? Of course. Yeah, so like u r, then you get, then you just get upon r and then partial theta of r hat, which is t hat, dot with t hat once again. That gives us the same, of course. So yeah, and then similarly you, okay, and you also get this other term. So you take the dot product of this thing with that thing, which is like what, partial ut upon r partial theta. Okay, so this is our divergence. Now you just have to check if it's 0 or not. I think it is, because look, uz is 0, so we don't care about that. Ur is also 0. Ut is the same thing as u, in fact, just the speed, right? Ur is 0 once again. Now partial u upon partial theta is 0, because even if you change your theta, your speed is not changing. So this is also 0, which means yes, our divergence is 0. So this is working out, right? So at least it passes one test. The vorticity being 0 is not a test, it's just something that you can use, right? So we don't care if the vorticity is 0 or not, right? So we don't need to do the curl operator, right? So yeah, this is it. Which means this looks like something that could actually happen. And since that is the thing, and yeah, it meets the boundary conditions as well. It meets the continuity equation, which was just this thing actually, right? So it meets that everywhere and looks good, no big deal. So now what that means is actually you can use this fluid flow that you have. So, you know, every block is moving with u tangentially, and just plug that. So just plug that fluid flow into this to get some stuff about pressure. So dv upon dt for any block as it moves, what's the dv upon dt? Just the acceleration, right? Which is of course just v square upon r. So just have the pressure and sorry, it's the density, right? That's the density, yes. The density, then you get the acceleration, which is v square upon r in the r negative r hat direction actually. Yeah, that, and actually I should say u square upon r, and the speed is same everywhere, so u square is kind of a constant in this case. Right, this thing we don't care about that because we are not moving along z in any case. So yeah, we don't care about this thing. Then minus del p, right? Of course this will actually have z components and everything, but we only care about the xy components. So this will just omit, and then similarly for del p will omit the z component, we'll only think about the xy component, just minus partial p upon partial x. Oh, okay, and also the gradient operator, we can also write that in the cylindrical form. So you know your partial, okay, yeah, this thing will just turn out to be this partial p upon partial r along the r hat direction plus partial p upon r partial theta along the t hat direction plus partial p upon partial z along the z hat direction. So yeah, this is actually very straightforward. It just becomes this thing. Awesome, right? But the divergence operator was not so straightforward, and the curl operator is definitely not straightforward. Anyway, so you get this thing, and this we don't have to worry about because we are only doing in the xy plane, right? Yeah, and also we can like assume this thing is 0. It is in fact, because there's no t hat component anywhere, right? So what assumption? It is 0. Yeah. So what it actually tells us is that this is just equal to what, negative partial p upon partial r in the r hat direction. Get rid of these r hats, multiplying by, sorry, taking a dot with r hat, right? You can do that, and yeah, it just leaves with this thing. So then, yeah, like partial p upon partial r, or just write it as dp upon dr, because in the context we know what we're doing, right? So this just becomes r dp upon dr. Okay, we not just don't do it fast forward. Okay, rho u squared upon r, and this will be just what, dr upon r is equal to dp upon rho u squared. Now just integrate this thing, so just get like natural log of r going from, let's just say R1 to R2. All right, and it's this thing. So P2 minus P1, just call this thing del P upon rho U squared. So if you're going from here, okay, so let's just say R1, this thing, call it R0 actually. So you have some pressure over there, right? Call that P0. So what this means is like natural log of, I did it correctly, right? Of course, this pressure should be higher. So as you increase your R, your pressure increases because of course the acceleration is in this direction. So you need pressure to be higher over here than here to actually push it centripetally, right? And that's why as you increase your R, your pressure should increase as well. So the natural log of R2, which is called R in fact. So just natural log of R upon R0, that's equal to P minus P0 upon rho U square. Or just put that over there. It's like rho U square and this thing. Right. So there you go. You got the distribution for this thing. Okay. So the ideal fluid flows along fine. So what do you have to figure out? The flow is steady. Are the pressure and velocity of the fluid equal at points 1 and 2? What was 1 and 2 though? Oh, these things. So one will have a higher pressure, two will have a lower pressure, and one will, okay, both have the same speeds though. So, right, the velocities are the same, but the pressures are not. And if someone presents with you a different solution to this thing, check if that works or not. And if it works, then just say, okay, this can have multiple solutions, right? Just throughout this, I'm going to do just that. I'm going to guess a solution and then see if that works or not. Because this involves 3 dimensions. How can I solve anything, right? So 150, what was this thing? 315, okay. 315, just write down our result, that's what we call it. So P is equal to P naught plus, and usually I reserve P naught for the atmospheric pressure, but then whatever. So what is a P1, right? Or let us say delta P, who cares? Okay, maybe not. So just P equal to P initial, right, plus rho U squared natural log of R upon R initial. That looks cool. Okay, next question. And U is same everywhere. Okay, then you have 316. Let's go. Two manometric tubes are mounted on a horizontal pipe of varying cross section at the sections S1 and S2. Okay, find the volume of water flowing across the pipe's section per unit time. So you want the volume flow rate. Okay, if the difference in water columns is equal to delta H. Oh, so like rho G delta H is the, and of course these columns are, yeah, like you use these columns to measure the hydrostatic pressure. And as I told you, you can do that because the Bernoulli's equation works for any 2 points in the fluid as long as there's no viscosity, right? Yeah. So just have like what, rho G delta H, that's the change in pressure. This is having higher speed, this is having lower speed, so this will have a higher pressure. So this is equal to what, P2 minus P1. Okay. What do you want, by the way? Find the volume of water flowing through the pipes section per unit time. Okay, the difference in water columns is equal to delta H. They didn't give us anything else. That's weird. And you maybe know what this thing is at least. There's no change in the G thing, or even if there is, it's actually very small change, right? We'll assume that, of course. Then this just becomes what? It's like negative half rho U2 squared minus U1 squared, right? Yeah, basically. Okay, interesting. And of course, you also have this thing U2 times. Wait, what happened? Why did this happen? Just wait a second. This should not have happened. mean, this is just going off. Oh, wait a second. Come on, work. Okay, I think we are back. Yeah, cool. Full screen. Fine. So you have this thing. What was I doing? Sorry. Right. The continuity equation, which is just u2 times s2 is equal to u1 times s1. How is this gonna give us anything? Is equal to q, of course. You can use this thing. So we'll just have u2 is equal to q upon s2, and also u1 equal to q upon s1, and just put that in there. So what this gives us is like rho g delta h is just equal to rho upon 2, and then u1 square minus u2 square, but then that is like q square 1 upon s1 squared minus 1 upon s2 squared, I think. Yeah. So what do you get? You just get like q squared times s2 squared minus s1 squared upon s1 squared s2 squared. That is equal to 2 delta h, or okay, that times of g, of course. So the q thing just becomes s1 s2 square root of 2 delta h g, so 2g delta h upon square root of s2 squared minus s1 squared. Yeah, that's the thing. So now we have the volume flow rate. Hey, you know what? Actually, you could use this everywhere that have the horizontal level. Okay, the same horizontal level. You can just use this everywhere, I think. Of course, this 2g delta h, instead of that, you just put the pressure change, 2 times the pressure change upon the density and everything. But whatever. This is what we got. Next question. 317. A pi sorry, what? A pitot tube. Okay, this is a new word for me. So I know what this is, but I never called it by this name. Right, figure 1.82 is mounted along the axis of a gas pipeline whose cross-section area is equal to S, assuming the viscosity to be negligible. And okay, find the volume of gas flowing across the section of the pipe per unit time. What? Sorry. A pilot tube is mounted along the axis of a gas pipeline, okay, whose cross-sectional area is equal to S, assuming the viscosity to be negligible, which means we can apply Bernoulli's equation everywhere. Okay, find the volume of the gas flowing across the section of the pipe. Oh, you just want Q, right? Yeah. Fine. If the difference in the liquid column is equal to delta H, and the densities of the liquid and the gas are this and that respectively. Okay, interesting. So you have what, like 3 points where you can apply this, right? You have this point and that point and this point. Except you don't know what this delta H is, so it's kind of weird, isn't it? You have some pressure over there and then, okay. Will it be the same pressure throughout? I don't think so. Uh, Not exactly what I should be doing. Okay, what about I just take this streamline which is running very next to this boundary, so that our, okay, there is still of course a change in H, right? Ah, there is always a change in H, isn't it? Not the pressure and stuff. I don't know. How do you even know the pressure though? I have no idea how to do that. Okay, just do it the proper way. So take any streamline, in fact, right? You have H depth like this, and then you have H plus delta H depth over here, right? Okay, like you will have a change in the pressure, sure. Bernoulli's equation you will have to apply. I know the pressure is being caused by the dynamic. What was the derivation? I just forgot everything. You will need like this point and something like this point or something. Can't I just use this and that? Okay, of course I can. That's gonna give us the change in pressure as a function of delta H. Sure. Okay, we'll see what happens. Just put in some values and see what we get. So applying the Bernoulli's equation at this point, and that point. So at this point, you have, I don't know what pressure you have. Just call it like P1. So just have P1, and this is at what height? So it's, okay, depth, I should say. So P1 minus rho g h. There's no speed, right? This is equal to what? At this point, you might have just P2. So P2 minus rho g h plus delta h. Okay, and it's equal to, so at this point, right? So that's our datum, by the way. And you have some pressure, we call this P, right? Which is the hydrostatic pressure. And then you also have the dynamic one, which is like half rho v squared. We get this thing. Sure. Interesting. Now what? Yeah, now what? What do we do now? Okay, that pressure is the same. Oh, you can also apply it like, just keep on applying it, and then, okay, these pressure things till this point and that point. Okay. Oh, this point and that point, they should have the same pressure, I think. Right? Wait, something's not correct on this thing. We are talking about a gas. We are talking about a gas. There is no rho. Density is very small. Oh, you should have known that. Sorry. Of course. Yeah, we should have known that. So density is like really small. So don't worry about that. That change in a rho, yeah, just don't worry about it, because density is very small in any case. So these factors don't matter. So there's just this pressure over there, there's this pressure over there. Just go up like this, and then you go up like that. Can you apply the Bernoulli's equation at this point and that point? Uh, are they connected by us? Okay, are they like part of the same fluid? It's getting kind of complicated. I mean, yeah, well, wait, if we apply that equation at this point as well as that point, oh, wait, you will run into a problem, because what you will get is actually that these pressures are the same, because, okay, are they a part of the streamline in the first place? They're not, right? No. And do these streamline have vorticity or something? Can you apply the Bernoulli's equation? You should be able to apply Bernoulli's equation, right? How do you apply it though? Well, here you just have the, you have some pressure over there, and that's just, okay. Okay, interesting. Okay, it's starting to not make sense now. Can you actually apply the Bernoulli's equation for this point and some point over here? So you have this scenario. So you have flow like this, and then you have this point. Can you apply the Bernoulli's equation between these 2 points? I mean, there's no streamline. There's no streamline connecting these two. Sure. So how do you get it done? Oh, uh, there's also this velocity stuff that we will have to worry about. It just gets a lot more complicated, right? Uh-oh. I think I got where we are going wrong. This is actually at zero velocity, right? Which means like there's viscosity throughout this, right? Yeah, I mean throughout this you have viscosity. Okay, and that's a problem, because now you can't apply the Bernoulli's equation everywhere. You can only apply it in the central region where there is low viscous forces. But that means that our manometer thing that we did the last time, you can't get the result from the Bernoulli's equation. So then how do we know that the pressure it measures is the hydrostatic pressure? Uh, Wait, This is not working. How do we know that that pressure it measures is in fact the hydrostatic pressure? Because if there's no, because if there are viscous forces, what that would mean is like this surface, so for this thing, this surface, it cannot have u equal to 0 because this is not having u equal to 0 unless this whole thing has u equal to 0, and actually what's happening is that it's kind of a gradient, and then this happens, right? So this is the our velocity profile, right? So there's 0, and then in the middle you have high velocities, and in this region viscous forces are 0 because the velocity is not changing all that much. In this region though there is a lot of viscosity, and at this point you have 0. Oh, okay, this is kind of complicated. I know how manometer, okay, I know what a manometer measures. I don't get it. How is this the pressure? How is this pressure the same as that pressure? Huh. So if this was not here, right? If this opening was not here, it would just be a wall, right? So what pressure would the wall get? Would it be the same thing as the hydrostatic pressure inside of this thing, or what? Okay, there's viscous forces. Just the changing velocity involved. What about the pressures though? You see these blocks, they only have forces along the x direction. They don't have forces along the y direction, right? So this volume element, it won't go in this direction. It will just continue moving forward. What that means is that there's no gradient of pressure in the y. Yeah, okay, right. Okay, that makes a lot of sense. Yes. Of course, as you move like this, I mean, first of all, your velocity in this direction is 0. So as you move like that, your um, only the viscous forces that act are because you have a gradient like this in the velocity, right? So your velocity in this direction, x direction, is changing as you move it along y. So you will have to take that into account. Okay, got it. And that will change your what, the speed, right? Yes. And what about the pressures though? The thing is like the pressure along this direction, so sorry, the velocity along this direction is 0 throughout, right? So the gradient, right, the gradient in that direction, right, just have del p upon del y. This thing will actually be 0 because del u upon del y, of course u y times that was 0, right? So yeah, wait, what was the thing once again? Let me see that once again. Oh, it should be u vector, sorry. So yeah, this was actually 0 because uy itself was, even though there's changing u vector, there's no y component, and uy is by itself just 0. So that will be 0 in any case, which means that whatever pressure is over here, the hydrostatic pressure, of course, it's the same hydrostatic pressure at this point. So the manometer still works out. See, I already told you it's a new thing for me because I have not gone into details like this yet, right? Uh, yeah, because until this point, I didn't have any kind of exposure to proper equations for the fluid, right? So I didn't have these questions popping in my head that why is the manometer working and when can we apply the Bernoulli's equation, and right. But now I do, and it's a lot more tough now. Okay, anyway, so this pressure is the same as the hydrostatic pressure, and that means our question that we did, it was correctly solved. No big deal. Okay, now let's. What question they were solving, by the way? 317. Right. So it's this thing. Of course, what that now means is that there's viscosity, so we can't just apply the Bernoulli's equation. That would be wrong. But this part, you can still apply this logic over there. That here you have zero velocity, and all the u vectors are complete in this direction, in the x direction. So there's no change in the y direction, which means that the pressure is the same throughout this column. So it's also same in this, like okay, close to this central region, or at some point in this central region, whatever hydrostatic pressure you have, it's the same pressure over here as well, which means that the pressure over here is just the hydrostatic pressure, or Okay, if it's a gas, is this going to be hydrostatic? I don't know. So yeah, the static pressure of, okay, that makes sense. Okay, it's just a static pressure. Okay, and okay, first of all, along this tube, as you go up, you have the same static pressure because rho is approximately zero. Uh, then in this region, you have some weird thing happening. You might have viscosity and everything. So how do you know that? Okay, like you have u equal to zero at this point. So how can you do this thing? The streamlines are going like this. They're avoiding this part. So then what's the pressure here? Is this actually equal to dynamic pressure or not? That's how the pi dot cube is used, right? To measure the dynamic pressure. But how would you know it is actually that? Hmm. Come on, think about it. Maybe like you can assume that no, you can't just go on assumptions. You know for sure that the speed over here, right, it's just zero throughout, right? Then at that point, it's definitely not, the streamlines can't be going in and out. That doesn't make any sense because of symmetry, right? There's a cylindrical symmetry to this thing, which means, okay, that's weird. So till that tip, right? Even at the tip, it's the same pressure and the flow speed is just zero. And then the flow speed zero region that actually comes out of the tube for some time. And then you will have like viscous forces acting over there. So once again, your Bernoulli's equation thing doesn't work actually. Huh, that was not good. But if the Bernoulli's equation doesn't work, then how can you get the dynamic pressure? Because the way we do that is we rely on the Bernoulli's equation thing. But if that doesn't work, there's no way we can say that the pressure inside is just a dynamic pressure. Or is there some way that I'm missing? Okay, so we know there's cylindrical symmetry, right? So over here you have u equal to zero. Just keep going. So there's this like streamlines are avoiding this region, right, where u is equal to zero. But then if you just keep going like that, right, you have some point over here. Okay, cool. And there's like viscous forces, which are, what exactly are these viscous forces doing? I don't know. Oh, okay, that's a problematic thing because if there's velocity gradient along this direction, that just means it's actually pushing it like that. That means there's a change in u in that way, and there's, oh god, viscosity is also contributing a change. Yeah, like viscosity is also contributing to the change in our u vector along this direction. Of course, that's a problem. It's really just a problem. How are we going to do this in that case? Along this streamline, it's not even a streamline in the first place because, oh god, okay, I don't want to be doing the proper 3D equations of this thing, and there's no justification for the fact that, okay, earlier I thought that Bernoulli's equation was applicable over here and I thought that was a good enough justification, but now it doesn't look correct because there's definitely viscosity involved, and that already invalidates Bernoulli's equation. We don't even need to show that the vorticity is not zero everywhere. Okay, it might not be, who knows. Already you have viscosity, which means you can't apply Bernoulli's. So the way it's usually done, it's just wrong, in fact. Right? It's wrong, of course. Unless this actually doesn't interact with the tube at all, in which case it would be actually correct. But that doesn't look very happening. Ah, okay. I didn't think I would get stuck once again, but I am here and I'm stuck. It's the same doubt that I got the first time when I tried to solve this question, and now it's once again coming. And hmm, we can't just assume that you have dynamic pressure, although that's what uh, we will do mostly. when solving actual question in the exam, but right now I want to do in proper detail. Now I don't see any way to do it without applying viscosity, and for that this equation is not enough. So you can't just rely on this equation. You will need the equation which involves viscosity as well to get the proper profile of u vector throughout this. Definitely not something I want to do. What other thing can you use? Sure, there might be like pressure, which is a gradient in the pressure, which is opposing that u vector thing. Okay, but we know that at some point, it must become u vector once again. When will that point occur? Right? That's the question. Divergence equal to zero. That doesn't actually mean that your u vectors should be zero in that direction completely. That's just not correct. It might have some components in that direction. Like it's, yeah, okay, that can happen for sure. Come on, think about it. So, okay, if I assume like it's cylindrical, it has cylindrical symmetry, then writing the divergence equation, what does that actually give us? It gives us partial u r upon partial r plus partial u z upon partial z, and this is the thing that we have to look for. So we don't know what this thing is yet. Okay, plus partial u. Okay, that doesn't matter because ut was zero in the first place. So don't look at that. What else you have? Plus ur upon r. Okay, this is equal to zero. That's what it's saying. The divergence of u being equal to zero. That's what it says, right? Okay. Uh, right. And what else do we know? Without viscosity, we can't solve this. That's the problem. I was thinking maybe there's some way that I can just link u, z, and p in some way without involving viscosity, but that doesn't look like it's going to happen. So then how do we do it? It's partial ur upon partial r might be something. Of course, it's changing, right? Yeah, ur upon r. Now I'm just stuck. I don't know what to do. Fine then. I think we should stop for now. I really wished we could continue this, but then now I will just have to do a bit of derivation before I can continue. I really didn't think we would have to go this far just to prove that something as simple as a Python cube works. Till now, okay, I've been just assuming that it works, right? That yeah, it's something that measures the dynamic pressure. I didn't think how it does it. Now when I do, it's not good. Okay, fine. Just stop here. So I'll see you in the next video.